The energy of projectile motion. Our project will focus on demonstrating free fall and its relationship with energy. In the presentation, we will be defining projectile motion and all mechanisms involved. The actual demonstration will involve throwing objects in the air to study the involvement of energy.
Projectile motion is an extension of free fall where an object moves exclusively under the influence of the Earth's gravity, which has a universal constant acceleration of 9.8 meters per second squared. An everyday example would be dropping a ball from arm length. The ball is accelerating down towards the ground as a result of the gravitational force acting on it. This is known as free fall acceleration.
When you throw the ball up in the air and watch it go down, the first portion is called projectile motion, where energy was used to launch the object upwards, indicating free fall into the second dimension. It refers to when an object is under the act of kinetic energy, where the energy is decreasing.
As the ball falls towards the ground, its gravitational potential energy is transformed into kinetic energy. The kinetic energy of the ball will continue increasing as the ball gains momentum, until it finally collides with the surface. When the ball collides, the kinetic energy is transformed into other forms of energy.
We hypothesize that energy will remain conserved and remain constant.
In projectile motion, the kinetic energy decreases when the ball goes up, while the potential energy increases. When the ball comes down, the kinetic energy increases and potential energy decreases. Throughout the whole motion, the total energy remains constant. It's only being converted from kinetic to potential.
For the demonstration, she threw the ball forwards at a downward angle. Because a projectile is an extension of free fall, we should expect it to follow the same rules with an equal initial and final velocity as the object remains under the force of gravity. The acceleration should also remain constant with 9.8 meters per second squared.
Energy will remain conserved, so initial energy will equal final energy. Our recorded initial energy was 21.4 joules, which was found via the sum of initial gravitational potential energy and initial kinetic energy of the launch. Therefore, the final energy will also be 21.4 joules, and because the point of the final energy will be when the ball is on the ground, the potential energy will be 0, and therefore the final energy will be determined solely by the final kinetic energy. The total energy line remains relatively constant with slight variability, which favors our hypothesis that energy is conserved. In addition, we calculated the actual final energy by using the recorded final kinetic energy, since potential energy will be 0 because the ball would be on the ground, giving us a value of 20.7 joules.
When comparing the predicted and calculated final energy, we use our two energies we have compared and isolated by taking those two, subtracting them, then dividing them by our calculated final energy, giving us 3.38%. Our prediction was within 5% of the true final energy, showing that our prediction is close to our true value.
Using the predicted final kinetic energy and its formula of 1/2 times mass times velocity, we were able to isolate the predicted final velocity, giving us a value of 8.28 meters per second. Our final velocity is 8.15 meters per second, which was found via the square root of the sum of its recorded x and y components.
In the same formula, such as the predicted and our actual final value for velocity, we take the two numbers we have calculated, subtract them from each other, then divide it by our final velocity, which giving us 1.60%. Our prediction was within the 5% of the true final velocity, showing that our prediction is close to the true value.
In conclusions, our results align with a prediction that energy is conserved throughout projectile motion. Any variation we observed between the predicted and actual results were from error in dot placement through the video analysis rather than the actual motion itself.